So now in this part we will continue with the file menu, as you can see from here. So the file menu functions, especially the correction table features, as you can see from here, and then we will move also to the home ribbon and its operational tools. So these functions are very important because they are affected the measurement accuracy, output behavior, and the meter setup verification during the testing. So let us start with the correction table from here. So simply you can import or export the correction table. Why do we need the correction table in the beginning? So in practical meter testing, the CMC can sometimes be used directly as a reference device during the load testing, and in this situation the measurement accuracy of the CMC itself becomes very important. So to improve this accuracy even further, the meter module allows us to something called correction table. So this correction table is basically a set of compensation values used to correct a small measurement deviations of the CMC itself. So these correction values are generated by comparing the CMC against a high accurate reference meter. So simply you can export this correction table. So this function is used after performing a calibration testing using a high accurate reference meter, as we said. And during this calibration test, the CMC output is compared against the reference meter readings. And at the end of the test, the measured correction values can be exported and stored as a correction table file. The exported file contains not only the correction values themselves, but also the serial number of the CMC and the measured test result, and this allows the correction table to be reused later with the same CMC. Also, you can import the correction table from here. So this function loads a previously saved correction table into the meter module, and it's saved in .ect, stands for error correction table. And once imported, the meter module automatically uses the correction values during the load testing whenever the CMC is acting as the reference device. So in simple words, the software compensates for a small measurement deviation of the CMC by applying imported correction values during the calculation, and this improves the final test accuracy while requiring an external reference meter during every test. Also, we have another option here. If you have already imported a correction table, you can unload this correction table. So the unload function of the correction table removes the imported correction table from the active test document. So this is useful when we want to reuse the same test setup but without applying any correction values. Before unloading the correction table, the existing test results should first be cleared from here, as you can see from here, to avoid conflicts between corrected and non-corrected results. Then we have the display correction table data here. So it allows you to view the actual correction values stored inside the table, and this is useful for verification purposes and helps the operator to confirm that the correction table has been loaded. So in summary, let's understand how the correction table is actually created. The process starts by connecting a CMC to a high accurate reference meter. As you can see here from the help button, so your CMC is connected to a test object, which is the meter under test, also with a reference meter. So the load test is performed using exactly the same voltage and current values that will later be used during the real testing applications of the test object. So this is important because the correction table only works for the exact test point stored inside it, and after the calibration test is completed, the result can be exported as a correction table. Later, this table can be imported back into the meter module, and when the correction table is imported, the values are automatically inverted and treated as a compensation values for the CMC measurement error. This means the meter module automatically adds these correction values during calculation in order to improve the final accuracy. One important tip here is to remember that the meter module doesn't interpolate between correction points. So only the exact voltage and current values stored inside the table will be corrected. Any other test points outside the stored values will remain uncorrected. So here is the help button. You can read it before using to import or export the correction table for your reference. Now that we understand the correction table functions, let us continue with the home ribbon and its tools. So the home ribbon contains several important functions, as you can see, which we can use before or during the testing. So this function helps the operator to control outputs, verify the meter behavior, determine the meter constants, and prepare the system before running automatic testing. So let us start with the quick access from here, as you can see. So selecting the quick access option here to stop the entire test after the test step that's assessed as failed. But please note that the quick access works in standalone mode only, which means if the meter is embedded in the control center test document like OCC file, the quick access is disabled. Then we have here the nominal voltage output. So this feature allows the CMC to continuously output the nominal voltage before and after the test execution. So the nominal voltage values are taken directly from the device setting section, and this function is always useful because many energy meters require stable voltage conditions before testing begins. By enabling the nominal voltage output, as you can see, the meter remains energized continuously even before the actual test starts, and this helps to stabilize the meter and reduces the startup effects. So when this option is enabled, as you can see, the nominal voltage is applied directly to the analog output of the CMC. If several test points are executed one after another, the voltage remains continuously active until the test table sends another control command that it changes the output conditions. Also, one important point here to understand the warm-up behavior. So if the test starts while the nominal voltage output is already active, the meter module doesn't apply additional warm-up time, and this is because the meter is already energized and stabilized. So the warm-up time is only applied when the test starts with the voltage output initially turned off. So to disable the nominal voltage output, we simply press the same button again. Now let us move forward to the static output function, which is one of the most important settings here also. So static output is mainly used for testing unknown meter, checking the pulse output or determining the meter constant. So unlike automatic testing, static output directly generates fixed voltage and current quantities without performing automatic timing evaluation or assessment. So this makes it very useful during the initial meter start setup and troubleshooting. Also here we have the find constant of the meter. This is one of the most common uses of a static output, is to determine the meter constant. This is especially useful when the meter constant is not known or when the operator wants to verify the actual pulse behavior of the meter. So to enable find constant, simply you can activate this box. Once enabled, additional field becomes available here, programmed pulse. So the first field is the pulse programmed. So here we can enter the number of pulses we want the software to count during the test. For example, we can ask the meter module to detect 10 pulses from the meter. Then also we can start the static output to detect the 10 programmed pulses. Also it will be displayed here in the detected pulses one by one. Now it's counting the startup time. As you can see, now it's detecting now the number of pulses until it reaches to number 10, which is programmed by ourselves. And then it will display here the pulse per quantity, which means pulse per kilowatt hour, for example. To deactivate, you can simply press the static output again to deactivate this box. Also here we have here the frequency. So if necessary, we can also adjust the frequency according to the actual operating frequency of the meter. So also we can start the static output as we explained by pressing the on button. The CMC starts to generate the selected voltage and the current at the same time, and the meter module begins monitoring the incoming pulses from the meter. Then it will detect here the number of pulses continuously, and the module will display this number of pulses received from the meter. And once the detected pulses match the programmed values, the software automatically calculates the meter constant and displays the result, as you can see from here. So this function is very useful during field testing because sometimes the meter nameplate may be unclear or damaged or unavailable. So in this situation, static output can help you to identify the actual pulse constant directly from the meter behavior. If you disable find meter constant, here you will have the generator setting. So when the find constant option is disabled, the generator setting section becomes active, and this allows you to manually generate voltage and current values. Here you can manually navigate to the voltage phase by phase, the current phase by phase, also the phase angle for the voltage and the current to change it manually and apply this new values to the energy meter. This allows you to simulate many different operating conditions directly from the CMC. And also we have here the cosine phi. As you can see, we have 3 fields for each phase. So as soon as the voltage and the current angles are exchanged from here, so the meter module automatically recalculate the cosine phi value, which is the power factor, and this helps you to verify the resulting power factor conditions based on the phase shift between the voltage and the current values. Then we have here the nominal button, and this nominal button resets all manually modified values back to their original nominal setting, and this is useful when the operator wants to quickly return to the standard conditions. Also here we have the vector diagram, which visually displays the vector and the current waveform together with their angular positions, and this gives you a quick graphical confirmation of the applied phase relationship, and especially useful when working with 3-phase systems or a phase angle adjustment. Then we have here the power section, and this power section displays the resulting active, reactive, and apparent power values based on the selected voltage, current, and phase angle settings. This allows you to immediately verify the generated power conditions. Also here we have the close button, which safely closes the static output window and turns off all the active outputs from the CMC. We also have here the help button, which opens the dedicated help documentation related to the static output function. Then we have here the test phase also. So when testing a single phase meter, the test phase selection allows us to choose which phase would be used during the testing. For example, if you navigate to the test object, and you can change the meter type to be a single phase as well. So you can get back again to the static output. Now it will allow you to check the L1 or L2 or L phase, or to select which phase you are currently generate the voltage and current to it. And this frequency, as we explained, allows adjustment between 10 Hertz up to 1000 Hertz. So by default, the nominal frequency will be entered here from the device setting automatically, as you can see. Here we have also values are. So these values are field shows whether the generated values are primary values or secondary values. And this helps the operator verify the currently displayed quantity in the meter itself. Then we have here the status. So the status field continuously displays the current operating condition of the meter module. For example, it may show, as we saw before, while testing the meter constant, it can show warm-up time, startup process, active generations, and so on. So now we have completed the file menu, also the home ribbon. So in the next part, we will continue the view ribbon as well, as you can see from here. So in this part, the view ribbon is a very integral part. Also the hardware setup and software configuration, we will navigate through one by one. And this is very important because correct hardware configuration is the foundation of a reliable and accurate testing. Also, even if all the parameters are configured correctly, the wrong hardware assignments or incorrect signal routing can completely invalidate the test result. So before starting any actual test, both the physical wiring and the software configuration should always be checked carefully. But before diving into the hardware configuration, let us continue the view ribbon from here, as we explained before. So it's the same as Test Universe modules view ribbon, but we have here one more or one additional feature, which is the result as accuracy. So one of the most important display options is the result as accuracies. So this option controls how the final test results are displayed inside the meter module and inside the generated reports. When results as accuracies enabled, the result column displays the meter accuracy in percentage. But for a single test run, the software directly shows the relative accuracy value. If multiple test runs are performed for the same test point, the meter module calculates and displays the average accuracy together within the standard deviation. So this gives you better understanding of the stability and the repeatability of the measurement as well. So when the result as accuracy is disabled, the result column displays the error values instead of accuracy values. Again, if a multiple test runs are performed, the software will calculate the average error together with the standard deviation. So some operator prefers working with error values directly, while others prefer viewing accuracy values. And the meter module always allows both display styles depending on your company practices or testing standards and so on. Now that we finished the result display setting, let us continue with the hardware setup and the signal assignment used by the meter module. As we learned from the Omicron Ohm's law, here is the second part. So simply you can select whatever CMC you are working with, like CMC 256 plus, for example. You can configure how many channels of voltage, how many channels of current to be used. Also, you can see here the wiring working flow from the configure button. Then you can navigate to the analog outputs. You can simply here define the 3 voltage output, the 3 current output. And in the most important tab here, which is binary / analog input, as you can see from here, you can see here we have a 10 multifunctional input, and we are using the external interface of the CMC 256 plus to be used as a counter, which means there is a scanning head positioned on the pulse LEDs to detect the number of pulses. So the counter input number 1 is used as a common, and counter input number 2 is used as a reference meter. And the operating frequency of this binary inputs is up to 10 kilohertz, but the normal binary input from 1 to 10 is up to 3 kilohertz. So if the meter have a binary output which is connected to binary input number 1, for example, you can simply select here the binary input number 1 as a counter, but it will give you accuracy up to 3 kilohertz only. But if you have external interface and scanning head, you can use the counter input number 1 and number 2 up to 10 kilohertz. So before running any test, the meter module must know exactly how the meter outputs are connected to the CMC inputs. This is only the most important setup, because the software depends completely on this assignment to correctly detect the number of pulses, also the output of voltage and current values. So by default, the meter module uses a predefined assignment between the meter outputs and the CMC inputs, as we explained. So normally the meter pulse output, or the MPO, is assigned to binary input number 1 on the front panel of the CMC, and this input can typically handle pulse frequencies up to 3 kilohertz, as we explained. But if you are using the counter inputs number 1 and number 2, so it can be used up to 100 kilohertz, and simply it can be used also as a reference meter. If you have RMPO, or a reference meter pulse output, it's usually assigned to the counter input number 2 to the real external interface of the CMC 256 plus.